Welcome to Quiet Universe. Today we're diving into something really wild. What if you woke up tomorrow and the Earth was flat? How would you even figure that out? Imagine looking outside and thinking, that horizon looks suspiciously flat. Suddenly, everything we've been so sure about, from gravity holding us down to the way the day starts and ends, would be completely flipped on its head. It's like someone decided to rewrite the rulebook just to mess with us. So, let's dive into this bizarre scenario and see just how quickly everything would stop making sense. So let's talk about gravity on a flat Earth, because apparently the universe decided to have a little fun with physics. On our nice, round Earth, gravity pulls everything toward the center, giving us that comforting sense of down. But on a flat Earth, things would get weird fast. Gravity wouldn't pull straight down. Instead, it would tug everything toward the center of the disk. Now, if you're lucky enough to live near the center, you might not notice too much difference. But the farther out you go, the stranger things would get. Imagine trying to live near the edge of the Earth, where gravity starts pulling at an angle. It wouldn't be a gentle slope. It would feel like the world is trying to slide you right off into the unknown. Walking would be more of an uphill battle, literally, and you'd probably find yourself clinging to trees or buildings just to avoid being dragged sideways. And forget about playing catch. Your ball would veer off course, not because of wind, but because gravity decided to mess with your game. Living on the edge would be like living in a funhouse, only instead of distorted mirrors, it's physics itself that's gone haywire. Imagine waking up tomorrow and discovering the Earth is flat. Forget everything you knew about how day turns into night. On this pancake-shaped planet, the sun's behavior would be the ultimate mystery. Instead of the sun rising in the east and setting in the west as we're used to, it would just, hover awkwardly above one side of the flat surface, leaving the other side in permanent darkness. Maybe it would do a strange loop-de-loop in the sky, trying its best to give everyone a bit of sunshine. But let's be real, it would be like trying to toast one side of a piece of bread without flipping it. Picture this. You're on the bright side of the world, basking in eternal daylight, sunglasses glued to your face, while folks on the other side are doomed to a life in the shadows. Trying to organize a Zoom call with friends on the other side? Good luck. They're stumbling around in the dark while you're squinting at your screen, trying to dodge the glare. Of course, we could try to imagine some kind of makeshift sun choreography, where the sun moves around like it's lost its GPS signal, desperately trying to give everyone a fair share of daylight. But even that doesn't solve the problem. With no consistent rotation, seasons would be a thing of the past, and our beloved time zones? A logistical nightmare. So much for that romantic notion of chasing the sunset or the tranquility of watching the sunrise. We'd all be left scratching our heads, wondering how we got into this bizarre, sunlit mess in the first place. Now, let's talk about seasons on our newly discovered flat Earth. Normally, we have seasons because of Earth's tilt and its orbit around the sun. But on a flat Earth, good luck making sense of that. Picture the confusion of trying to explain why some parts of this pancake Earth would experience summer while others are bundled up for winter. Maybe the sun would play favorites and hover over one spot for months, cooking one half of the world like a griddle while the other half shivers in an endless winter. The sun would have to zigzag back and forth, desperately trying to provide a semblance of seasonal change, like some kind of cosmic waiter who can't figure out which table ordered summer. Imagine telling someone in Australia that it's their turn for summer, but the sun is running late because it got stuck in traffic over Europe. Meanwhile, Europe is having the longest summer ever, and no one knows if it's ever going to end. Forget trying to plan a vacation or a simple barbecue. Mother Nature's whole schedule would be out the window. And let's not even start on the poor farmers trying to figure out when to plant their crops. Spring? Autumn? Who knows? Without the Earth's tilt, the entire concept of seasons would be as flat as our new world, leaving everyone scratching their heads and praying for a miracle to bring back some predictable weather patterns. Seasons would become a chaotic lottery, with no rhyme or reason, and we'd be left wondering if we somehow stumbled into an alternate reality where Mother Nature forgot how to do her job. Now let's dive into the delightful chaos of time zones on a flat Earth. Time zones work because the Earth is round and spins on its axis, giving us sunrise in one place while another place is still fast asleep in the dark. But on a flat Earth, forget about it. Imagine trying to figure out what time it is when the sun isn't behaving like it should. Is it noon in New York? Or is it the same time as midnight in Tokyo? On a flat Earth, The sun might just wander around aimlessly, popping up wherever it feels like, without any sense of direction or urgency. Maybe it decides to hang out over Europe for a while the rest of the world waits impatiently, wondering when they'll get their turn for daylight. Picture trying to set up a meeting with colleagues in different time zones. You send out the invite, and everyone shows up at different hours, confused and grumpy. Some are still rubbing the sleep from their eyes. Others are ready for lunch, and a few are wondering if they should just go back to bed. The concept of time would become a free-for-all, and you'd never know if you were running late or early. Because hey, who can tell when the sun doesn't have a clue where it's supposed to be? And then there's travel. If you thought jet lag was bad before, just wait until you're trying to adjust to the flat Earth's version of time. You'd never know what time it is when you land, or even if the sun will be up when you get there. It would be the ultimate nightmare for anyone trying to keep a schedule, with every place on Earth stuck in its own weird time warp. So much for coordinating a simple phone call across continents. On a flat Earth, the idea of time zones would be about as useful as a chocolate teapot. Now let's tackle the mystery of ships disappearing over the horizon. On our round Earth, this is a straightforward bit of physics. As a ship sails away, it gradually dips below the curve of the Earth, disappearing hull first. It's almost poetic how the world seems to swallow it up. But on a flat Earth, things would get a bit more magical. Picture standing on the shore, watching a ship head out to sea. On a flat Earth, you'd expect to keep seeing that ship shrink into a tiny, like some never-ending magic trick, until it was so small that you'd need binoculars just to catch a glimpse. After all, with no curve to hide behind, where else could it go? Yet, funny enough, that's not what we see. Instead, that ship steadily sinks out of sight, as if it's got a secret agenda to join an exclusive party below the horizon. Something that just shouldn't happen on a flat plane. Imagine trying to explain this one away. Oh, maybe the ship is just playing hide and seek, you might joke. Or perhaps it's just tired of being seen and decides to dip into the mysterious abyss of the flat Earth. Or, better yet, maybe the ocean is just one big optical illusion, bending light and making things disappear like a cheap carnival mirror. But none of these theories quite hold water, do they? And let's not forget the sailors themselves, who might be wondering why their ships seem to vanish as if slipping over the edge of the world. Are they secretly part of some grand conspiracy, and on the act to keep us all fooled? It would be quite the production. Thousands of mariners, all nodding in unison, saying, "Yep, we disappeared again, just like we're supposed to." In reality, the disappearing hulls tell a simple story. The Earth isn't flat. The horizon line is like nature's curtain call, dropping to remind us of the beautiful curve of our planet. No smoke and mirrors. No secret societies of ship captains pulling pranks, just good old-fashioned physics at work. Let's dive into the wild world of circumnavigation on a flat Earth. On our round planet, you can hop on a plane, fly in a straight line, and eventually end up right back where you started. Simple enough, right? But on a flat Earth, the whole idea of flying around the world turns into a comedy sketch. Imagine packing your bags for an epic trip around the globe, only to realize halfway through that you're not looping back to your starting point, but rather heading straight off in well, who knows where. Maybe you just keep going and going, like a character in a bad cartoon, until you reach the edge of the Earth and fell off into space. Or perhaps you'd end up bumping into some mysterious wall that marks the end of the world. Sounds like the plot twist of a sci-fi movie, doesn't it? Try explaining to someone how Magellan and all those other explorers managed to make it back home without a spherical Earth. Did they just turn around at some point and hope no one noticed? Or maybe they sailed to the end and then did a quick U-turn pretending they went all the way around. Yep, definitely went around the world, they'd say, casually hiding the fact they just went out and back. Think about pilots too. They're flying in what they believe to be a straight path, only to end up right back where they started. On a flat Earth, they'd probably just circle aimlessly, looking down and wondering why the heck they keep seeing the same landmarks over and over again. Not to mention the GPS systems would be utterly confused, with satellites supposedly hovering above a flat plane, frantically recalculating as planes keep flying off into oblivion. In reality, the beauty of circumnavigation is proof of Earth's curvature. You can literally set sail or take flight and, without turning around, find yourself right back home like magic. Except it's not magic, it's science. The spherical Earth makes it all possible, while a flat Earth would turn every globetrotter's dream into an endless, flat-out nightmare. Now, let's talk about air travel on a flat Earth. On our round planet, pilots follow what's called Great Circle routes, the shortest path between 2 points on a sphere. It's like magic. You hop on a plane in New York, and it swoops over the Arctic to get you to Tokyo faster. But on a flat Earth, buckle up because those flight paths would get bizarre real quick. Picture yourself booking a flight from Los Angeles to Sydney. Normally, you'd fly over the Pacific, nice and straightforward. But on a flat Earth, who knows where you'd end up? Maybe the plane would make a sharp detour over Europe, swing by Africa for a quick hello, then loop around Asia before finally heading south. Because why not? Without the logic of a spherical Earth, everything's up for grabs. Imagine the announcements from the cockpit. Ladies and gentlemen, this is your captain speaking. Due to our flat Earth, we'll be taking the scenic route over Antarctica. We're not entirely sure how long the flight will be, but sit back, relax, and enjoy the endless detours. And don't even think about fuel efficiency. Planes would be zigzagging all over the place like some kind of drunken bird trying to figure out which way is home. And then there's the flight tracker on the back of your seat, usually a comforting little graphic showing you inching towards your destination. On a flat Earth, it would be a chaotic mess. Your plane icon might dart all over the screen, making random pit stops on the way. You might even wonder if the pilot is lost or if this is all some elaborate prank. Of course, airlines would love this setup. Think of all the extra tickets they could sell as flights mysteriously take twice as long to get anywhere. But for the rest of us, it would be a logistical nightmare. The reality is that flight paths make perfect sense on a spherical Earth. Great Circle routes are efficient and straightforward, not some tangled web of guesswork and confusion. So, next time you're on a flight, you can thank the curved Earth for making sure you don't end up taking the grand tour of the world just to get across the ocean. Let's gaze up at the night sky and ponder how things would look on a flat Earth. On our round Earth, the movements of planets, stars, and constellations are a beautiful cosmic ballet, all perfectly explained by the planet's spherical shape and its rotation. But if the Earth were flat, well, we'd be in for quite a show, but not the kind anyone would pay to see. First off, let's talk about the constellations. On our spherical Earth, we see different constellations in different hemispheres. If you're in the northern hemisphere, you get to enjoy the Big Dipper and Polaris. Meanwhile, folks down in the southern hemisphere are checking out the Southern Cross. It's a neat way to make you feel like there's more to the universe than your own backyard. But on a flat Earth, good luck explaining why half the world would be looking up at the sky and seeing something entirely different. Maybe the flat Earth would have to come up with some sort of cosmic peekaboo game, where half the sky is hidden behind a giant celestial curtain, just to keep things interesting. And what about the planets? On a spherical Earth, we understand how they orbit around the sun, creating predictable patterns that have been mapped out for centuries. But on a flat Earth, imagine trying to explain how celestial bodies would orbit around. What, exactly? A big flat disk floating in space? Would the sun just do laps around the edge of the Earth, like some deranged race car driver? Or maybe the planets would all just kind of float around aimlessly, unsure of where they're supposed to be going. And think about all those amateur astronomers who spend their nights tracking the movements of stars and planets. On a flat Earth, their star charts would be as useful as a GPS with no signal. Tonight, we should see Mars. Oh wait, never mind, it's decided to do a random loop-de-loop instead. Who knew? Not to mention, we'd have a hard time explaining why we have day and night at all. On a flat Earth, the sun would probably need a very creative routine, like a DJ at a party who keeps trying to mix things up but ends up creating a chaotic mess instead. In reality, the night sky is predictable and orderly because of the spherical shape of our planet. The constellations make sense, the planets move in understandable orbits, and astronomers can actually do their jobs without needing to invent new physics every night. On a flat Earth, the heavens would be a jumbled mess, leaving us all scratching our heads and wishing for some cosmic clarity. Let's talk about satellites and their orbits. On our wonderfully round Earth, satellites zip around in neat little paths, thanks to the planet's gravity holding them in place. It's a simple, elegant system that lets us enjoy things like GPS, weather forecasts, and binge-watching shows on streaming services. But on a flat Earth? Oh boy, satellites would be in for a wild ride. Imagine launching a satellite on a flat Earth. Instead of smoothly orbiting the globe, it would be more like a chaotic game of pinball. You'd have to constantly dodge mountains, skyscrapers, and maybe even a few confused birds. And without a spherical Earth's gravity to keep them in line, these satellites would be drifting all over the place like lost balloons. not so much orbiting as meandering aimlessly through space. Picture engineers trying to explain this. Yeah, we just launched our new communication satellite, but it seems to be doing a leisurely loop around the flat Earth. We're not sure when it'll be back overhead, so don't hold your breath for a strong signal anytime soon. Good luck trying to keep your favorite show from buffering with that setup. And think about the International Space Station, which orbits the Earth about every 90 minutes. On a flat Earth, the astronauts would need to brace themselves for a roller coaster ride. Instead of gliding smoothly around a curved planet, they'd be whizzing back and forth across a giant dinner plate, probably feeling like they're stuck in some bizarre sci-fi theme park ride. Without the Earth's gravity acting like a cosmic tether, we'd have to come up with some creative ways to keep satellites from floating off into deep space or crashing down. Maybe we just tie them down with giant ropes, anchoring them to various countries. Sorry, Europe, you're on weather satellite duty today. Try not to let it drift over to Asia. In reality, satellite orbits work perfectly because of the Earth's spherical shape and its gravitational pull. It's a delicate dance that requires just the right balance of speed and gravity, something that makes absolutely no sense on a flat Earth. So, next time you check the weather or use your GPS, you can thank the round Earth for making sure satellites don't fly off into who knows where. Let's dive into the wonderful world of weather, specifically the Coriolis effect. On our spherical, rotating Earth, the Coriolis effect is what gives us those spinning storm systems and swirling ocean currents. It's the reason hurricanes twirl in one direction in the northern hemisphere and the opposite in the southern hemisphere. But on a flat Earth? Well, weather forecasting would be more like rolling dice and hoping for the best. Imagine waking up to check the weather on a flat Earth. Instead of a helpful forecast, you'd get something like, "Today, we have absolutely no idea what's going on. Expect some chaotic winds, a surprise downpour, and maybe a cyclone or two that just decided to form out of nowhere. Good luck out there." Without the Coriolis effect, air and water would move in straight lines, leaving us with a hodgepodge of unpredictable weather patterns. Forget about the nice, orderly systems we're used to on a flat Earth. It would be weather anarchy. Picture meteorologists trying to explain this new reality on the evening news. Well, folks, without the Earth's rotation causing the Coriolis effect, we're not really sure why that giant storm is spinning like it is. Maybe it's just in a bad mood. Or perhaps the ocean got bored and decided to send a rogue wave your way. Who knows? And then there are ocean currents. On a round Earth, the Coriolis effect helps create predictable ocean currents that regulate climate and marine life. On a flat Earth, those currents would be completely confused, like they're trying to navigate a giant maze with no exit. Warm water would slosh around randomly, creating boiling hot spots in some areas and freezing others. Fish would probably be just as baffled as we are, swimming around in circles, wondering where all the normal currents went. Let's not even get started on planes. Without the Coriolis effect, pilots would have to deal with random wind patterns that could change direction on a whim. One minute you're cruising along, and the next, you're facing a headwind from out of nowhere. Ladies and gentlemen, we're experiencing some unexpected turbulence, probably because the wind has decided it doesn't know which way to blow today. In reality, the Coriolis effect is a vital part of our planet's atmospheric dynamics, helping to create the weather patterns and ocean currents we rely on. It's all thanks to the Earth's rotation and curvature. On a flat Earth, we'd have to throw all our weather maps and models out the window and just hope for the best. So, the next time you're grateful for a sunny day or a nice breeze, just remember that it's all made possible by the spinning, spherical Earth we call home. Let's talk about the countless images of Earth taken from space. You know, those beautiful photos showing our planet as a big, blue, and unmistakably round ball. On a flat Earth, we'd have to toss all of those out the window and come up with one heck of an explanation for what we've been seeing all these years. Imagine trying to explain away every single image of our spherical planet. According to flat Earth logic, every astronaut, satellite, and space agency is apparently in on some grand conspiracy. That's right, thousands of people from different countries, all agreeing to keep this massive secret about the shape of the Earth. They must have the best-kept secret pact ever. No one has slipped up in decades of space exploration. Picture NASA's daily morning meetings if the Earth were flat. Okay, folks, remember, no talking about the real shape of the Earth. And don't forget to Photoshop those round planet pics before sending them out to the public. We can't let them know the truth. Can you imagine the kind of coordination this conspiracy would require? They'd need a full-time team just to make sure all the images match up and not one single person forgets their lines in this global charade. Then there's the astronauts. They train for years, risk their lives going into space, And what do they do up there? Spend all their time taking fake photos of a round Earth to keep up the illusion. I bet that's what they dreamed of doing as kids, becoming part of a vast cover-up rather than exploring the cosmos. When Neil Armstrong took that famous step onto the moon, he must have been thinking, one small step for man, one giant leap for maintaining the lie. And think about all the satellites up there, supposedly orbiting around Earth. On a flat Earth, they'd just be taking circles above a disk. And those orbiting pictures? Just more fabricated images to keep the story going. Every space agency, from NASA to the European Space Agency to SpaceX, would have to be in on it, spending billions of dollars to perpetuate this illusion for. Well, for no clear reason, really. In reality, these photos from space are clear, beautiful proof of our round Earth. They're the result of years of scientific achievement and exploration. So, the next time you see an image of Earth from space, you can rest assured that it's not part of some elaborate prank. It's just what happens when you take a picture of a spherical planet from above. So, imagine you wake up tomorrow and the Earth is suddenly flat. Let's start with moon phases and eclipses. On our round Earth, the lovely ballet between the sun, moon, and Earth gives us those beautiful lunar phases and awe-inspiring eclipses. You know, the ones people travel miles to see. But on a flat Earth, you'd have to kiss that logic goodbye. Picture this. You're at a flat Earth party, because apparently that's a thing now, and someone tries to explain why the moon changes shape. They might tell you it's some mystical shadow from an unseen object, or, better yet, that the moon is just trolling us with its phases. As for eclipses, well, good luck explaining how a flat Earth can perfectly align to create those. It's like trying to cut a perfect circle out of a pancake. You can try, but it's not going to look right. But hey, in this flat Earth world, you could just chalk it up to flat physics, where shadows move in mysterious ways, and the universe just works differently because why not? The truth is, explaining moon phases and eclipses on a flat Earth would probably require some mental gymnastics that would make the Olympics proud. It's almost as if the universe is telling us, stick to what works, spheres, not pancakes. So, you're on your morning hike with your trusty compass, which has always pointed you in the right direction. North, obviously. But suddenly, you're living on a flat Earth. You glance down, and your compass is spinning like it's auditioning for a circus act. Why? Because the Earth's magnetic field, the one we've relied on for ages, just wouldn't play nice on a flat world. On our spherical Earth, the movement of molten iron within the core creates a magnetic field, complete with magnetic poles that guide our compasses. It's like having a built-in GPS, minus the satellites. But on a flat Earth, this system would be about as reliable as a Wi-Fi signal in a dead zone. The idea of magnetic poles on a flat plane is like trying to stick a magnet on a pancake. Sure, it might stick in a few spots, but good luck getting a consistent pull. In navigation? Well, you probably need a new strategy, like maybe following the sun and hoping for the best. The concept of north would be as elusive as a decent Wi-Fi password, leaving explorers and anyone trying to find their way completely lost. So, unless you're in the mood for some seriously confusing travel plans, you might want to stick with a round Earth where magnetic poles actually make sense. Imagine you're climbing a mountain, enjoying the view, and suddenly you notice breathing is getting harder. No big deal, right? You're just experiencing the drop in atmospheric pressure that happens as you gain altitude. But wait, what if the Earth were flat? In that case, you'd probably be scratching your head, wondering why the air isn't equally thick everywhere. On our round Earth, the atmosphere wraps around the globe, and as you go higher, there's less air above you, which means less pressure. It's a simple, elegant system that just works. But on a flat Earth, that whole setup becomes a bit of a mystery. Why would air pressure decrease as you go up if the atmosphere were just hanging out on a giant pancake? Maybe the air is just being difficult, deciding to get thinner for no good reason other than to mess with mountain climbers. Or maybe, in this flat world, atmospheric pressure would be as unpredictable as a cat's mood. One minute you're breathing easy, the next you're gasping for air. Who knows? The consistent decrease in pressure with altitude would be a hard thing to explain without a spherical Earth. You'd have to start making up some pretty wild theories, like maybe the atmosphere is just really lazy and doesn't feel like hanging around up high. In reality, the consistent change in atmospheric pressure makes perfect sense on a round Earth. On a flat Earth, though, good luck figuring that one out without turning your hike into a bizarre science experiment. So, you're sitting there trying to watch your favorite TV show, but all you get is static. You check your phone, no signal. The GPS? It's spinning like it's lost in space. Welcome to the Flat Earth, where global communication is about as reliable as a game of telephone played across continents. On our wonderfully curved Earth, signals like radio, TV, and GPS bounce and travel thanks to the Earth's shape and atmosphere. The curvature helps these signals reach far and wide, wrapping around the globe like a cozy blanket of connectivity. But on a flat Earth, well, things get a bit flat. Without the Earth's curvature, signals would struggle to get from point A to point B. Radio waves might just keep going until they fall off the edge, assuming there even is an edge, and GPS would be about as trustworthy as asking your dog for directions. You'd probably have zones where communication is a hit or miss, and crossing time zones would feel like stepping into another dimension where Wi-Fi is a distant memory. Imagine trying to stream a video or send a message across the globe. Good luck with that. Signals wouldn't know where to go or how to bend around obstacles because the whole system is based on a planet that's, well, not flat. The atmosphere wouldn't play nice either, making sure that even if you managed to get a signal, it would be spotty at best. In short, if the Earth were flat, global communication would be a mess. You'd be better off with smoke signals or carrier pigeons. At least they don't rely on a round Earth to get the job done. Imagine you're outside on a sunny day, casting a shadow that stretches out in front of you. Now, you're smart enough to know that shadows have a mind of their own. They change shape depending on the angle of the light and your position on Earth. But in a flat Earth scenario, shadows would become the ultimate pranksters. Let's start with lunar eclipses. Normally, when the Earth gets between the sun and the moon, it casts a nice, round shadow on the moon. This is because our lovely spherical Earth blocks the sunlight in a way that makes perfect sense. But on a flat Earth, that round shadow would be a hard thing to explain. Maybe the flat Earth has a secret third dimension that only comes out during eclipses, just to mess with us. Now think about those shadows you cast at different latitudes. On a round Earth, the curvature and tilt of the planet create all sorts of interesting shadow effects. At the equator, shadows are short and squat. Closer to the poles, they stretch out like they're trying to escape. It's all due to the Earth's curvature playing with light. But on a flat Earth, what's the excuse? Maybe shadows just get bored and decide to do their own thing, ignoring the rules of physics entirely. In reality, shadows behave the way they do because we live on a spherical planet. The consistency of those shadows, whether it's the Earth's shadow on the moon or the one you cast on the ground, all makes sense in a round world. On a flat Earth, though, shadows would be as confusing as trying to find logic in a funhouse mirror. So, you're gazing up at the night sky, marveling at the stars, and you notice something intriguing. Some of them seem to shift ever so slightly against the backdrop of more distant stars as the months go by. That's parallax, a nifty little trick of perspective that happens because our Earth is moving around the sun. But on a flat Earth, well, let's just say the stars would have a bit of an identity crisis. Parallax relies on the fact that as the Earth orbits the sun, it's in a different spot every few months, giving us a fresh angle on those nearby stars. It's like looking at an object first with one eye, then the other. The shift in perspective is obvious. But on a flat Earth, good luck with that. Without an orbit to change our vantage point, parallax would be about as believable as a magician's disappearing act. Pretty to watch, but impossible to explain. In a flat Earth scenario, you'd have to come up with some wild theories to explain why stars appear to move against the background of the cosmos. Maybe they're just really fickle, deciding to wander around for no reason at all. Or perhaps the universe is playing an elaborate joke on us, making it look like we're moving when really, it's the stars that are doing all the work. But in the real world, star parallax is a straightforward consequence of living on a round, orbiting Earth. It's a simple, elegant proof that we're not standing still. On a flat Earth, though, parallax would be a mystery wrapped in an enigma with no logical explanation in sight. Just another reason why a flat Earth makes about as much sense as trying to measure distance with a rubber band. So, you're standing at the foot of a majestic mountain, maybe even staring into the mouth of a volcano, and you wonder how these colossal features came to be. On our spherical Earth, it's all thanks to the dance of tectonic plates, those massive slabs of rock that slowly shuffle around, bumping into each other and giving us mountains, volcanoes, and the occasional earthquake. But if the Earth were flat, well, we'd have a bit of a geological mystery on our hands. Plate tectonics works because the Earth is a sphere. The plates float on a layer of molten rock, and as they move, they crash together, pull apart, and slide past one another. These interactions create everything from the Himalayas to the Pacific Ring of Fire. But on a flat Earth, suddenly, those plates would need a new job description because the whole process would be out the window. You'd have to invent some entirely new mechanism to explain how mountains and volcanoes could form on a flat plane. Maybe the ground just gets really mad in certain spots and decides to rise up and protest. Or perhaps there's a giant underground mole pushing things around to keep us on our toes. The point is, without a spherical Earth and the movement of tectonic plates, the existence of mountain ranges and volcanoes would be as perplexing as why anyone would believe in a flat Earth in the first place. In the real world, these natural wonders are the result of millions of years of tectonic activity, all perfectly explained by the Earth's round shape. On a flat Earth, though, you'd be left scratching your head, trying to come up with a reason why the ground suddenly decided to pile itself up into mountains or spew molten rock into the sky. It would be like trying to explain why your flat pizza suddenly has a crust that's a mile high. Just doesn't add up. Imagine you're in a museum, watching a Foucault pendulum, a giant swinging ball that slowly shifts its plane of swing as time passes. It's a simple yet powerful demonstration of the Earth's rotation. But if the Earth were flat and didn't rotate, well, that pendulum would be doing some pretty confusing tricks. On our round, rotating Earth, the pendulum swing rotates because the ground beneath it is moving. The Earth spins, and the pendulum, swinging in its own plane, reveals that motion. But on a flat, non-rotating Earth, you'd have to explain why this pendulum has suddenly decided to develop a mind of its own and start twisting its swing for no apparent reason. Maybe in this flat world, pendulums are just temperamental. One day they swing back and forth. The next day they decide to mix it up and start rotating their path just to keep things interesting. But that's hardly a scientific explanation. Without Earth's rotation, there's no logical reason for a Foucault pendulum to behave the way it does. In reality, the Foucault pendulum's shifting swing is a clear and undeniable sign of Earth's rotation. It's one of those experiments that beautifully ties everything together: motion, gravity, the shape of the Earth. On a flat Earth, though, you'd be left wondering why this pendulum won't just stick to a simple back and forth, instead of mysteriously twisting like it's auditioning for a spot in a magic show. Imagine packing for a world trip. You start in the tropics, sweating under the blazing sun, then head north to the temperate zones, where you finally get to wear that light jacket and end up shivering in the polar regions. This neat variety of climates is all thanks to the Earth being a sphere with an axial tilt that creates different climate zones. But if the Earth were flat, well, good luck figuring out why you'd need both a bikini and a parka. On our spherical Earth, the sun's rays hit different parts of the planet at different angles because of its shape and tilt. That's why we have warm, sun-soaked tropics, milder temperate zones, and frigid polar regions. It's a system that makes perfect sense. But on a flat Earth, explaining why it's blazing hot near the equator and freezing at the poles would be about as easy as explaining why your flat-screen TV only shows certain channels based on where you're sitting in the room. In a flat Earth scenario, you'd have to invent some wild ideas to explain these temperature and daylight differences. Maybe the sun has a weird habit of focusing its heat on certain spots while ignoring others, just to keep things interesting. Or perhaps the atmosphere is playing favorites, giving some areas endless sunshine and others the cold shoulder. But in the real world, the Earth's spherical shape and axial tilt create a beautifully logical pattern of climate zones. On a flat Earth, though, you'd be left scratching your head, wondering why the weather is so random and what on earth you're supposed to pack for that trip across the planet. Picture yourself on a chilly night, gazing up at the sky as the northern lights dance in a swirl of greens and purples. It's one of nature's most stunning light shows, and it happens because of the Earth's magnetic poles interacting with the solar wind. But if the Earth were flat, well, the auroras would become a bit of a head-scratcher. On our round Earth, the magnetic field guides charged particles from the sun toward the poles, where they collide with the atmosphere and light up the sky. The auroras appear near the poles because that's where the magnetic field is strongest. But on a flat Earth, the idea of magnetic poles would be as murky as trying to explain why your GPS is acting up. In this flat Earth scenario, you'd have to come up with some pretty creative explanations for why these lights only show up near the edges of the world. Maybe the solar wind particles have a GPS of their own and just know where to go, or perhaps the atmosphere has secret light-up zones that it activates for a good show. But in reality, the auroras are perfectly explained by the Earth's magnetic field and its interaction with solar particles. They're exactly where you'd expect them to be, near the poles, thanks to the Earth's spherical shape. On a flat Earth, though, you'd be left wondering why the lights only seem to show up in certain places, as if the sky were saving its best tricks for the far corners of the world. Imagine waking up tomorrow to discover that the Earth is flat. Suddenly, the smooth curve of the planet that has dutifully helped radio waves travel vast distances is gone. Remember that long-distance radio transmission we've relied on? Yeah, that's about to get weird. On our curved Earth, radio waves get a helpful boost from the planet's curvature and the ionosphere, which reflects those signals back down, enabling global communication. But if the Earth were flat, those signals would just shoot off into space or hit a wall. If there's an edge, of course. Say goodbye to chatting with someone on the other side of the world or tuning into your favorite station from across the country. Without the curvature to guide those signals, you'd be lucky to hear anything beyond your neighborhood. So, while we'd be grappling with a lot of other bizarre changes in a flat Earth scenario, you'd also be hunting for a good old-fashioned carrier pigeon, because that smartphone would be as useful as a brick. So, you wake up tomorrow and the Earth is suddenly flat. First, you'd probably look around and wonder how your coffee is still staying in the cup. But then, you'd notice something far more inconvenient. Your GPS is completely useless. See, GPS is this nifty system that depends on satellites orbiting our nice, round Earth. These satellites work together to pinpoint your location using the curvature of the planet, like some high-tech cosmic dance. But on a flat Earth, that choreography falls apart. The satellites would have no idea how to function in this two-dimensional mess. And good luck getting them to triangulate your position when the entire concept is based on a spherical Earth. In short, you'd be trying to find your way to the grocery store with a map that doesn't make sense anymore, while your phone insists you're somewhere in the middle of a non-existent ocean. Suddenly, you're back to navigating by the sun and hoping you remember which way is north. Picture this. You wake up tomorrow to find out the Earth is flat. Exciting, right? Well, not when you consider the chaos it would unleash on our oceans, specifically those grand circular currents known as gyres. On our trusty spherical Earth, these gyres perform a delicate ballet, orchestrated by the planet's rotation and the Coriolis effect. The Earth spins, creating this invisible force that deflects moving objects like ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere. This results in those massive, predictable circular patterns that help regulate climate, distribute nutrients, and even influence weather systems. Now, let's flip the script. On a flat Earth, the fundamental mechanics that drive these gyres simply vanish. Without the Coriolis effect, those ocean currents would lose their directional bias. Imagine trying to maintain those perfectly balanced loops without the Earth's spin to guide them. It's like trying to spin a basketball on a perfectly still table. Sure, it might work for a second, but it won't last long. The absence of a spherical shape would further complicate things. Gyres rely on the curvature of the Earth to maintain their paths. On a flat plane, there's no natural boundary to keep these currents looping consistently. You'd end up with chaotic, unpredictable water movements that make no sense, leaving marine scientists utterly baffled. Navigation would become a nightmare. Ships depend on reliable current patterns for efficient routing. Suddenly, charts and maps would be unreliable, and crossing oceans would feel like steering a boat through a whirlpool of confusion. Moreover, the disruption wouldn't stop at navigation. These gyres play a crucial role in regulating global climate by distributing heat and moisture around the planet. Without their orderly circulation, weather patterns would become erratic. Expect more extreme weather events, unpredictable rainfall, and perhaps even the complete collapse of ecosystems that depend on these stable currents. In essence, declaring the Earth flat would turn our oceans into a chaotic mess, dismantling the very systems that keep marine life thriving and our weather somewhat predictable. So, while the idea of a flat Earth might seem intriguing at first glance, the ripple effects on something as fundamental as ocean gyres reveal just how indispensable our planet's true shape really is. Imagine waking up to a flat Earth and then realizing you have to rethink everything, including earthquakes. Those rumbles under our feet? They become a whole new kind of mystery. In the real world, when an earthquake hits, it sends seismic waves rippling through the Earth. These waves behave in very specific ways because they're traveling through a round planet with layers, crust, mantle, core. As they move, they reflect, refract, and bend depending on what they hit. This is why seismologists can tell so much about an earthquake's origin and the Earth's internal structure. Now, If the Earth were flat, those seismic waves wouldn't know what to do with themselves. The reflection and refraction that we see today, gone. Instead of neatly curving around the Earth, those waves would just scatter aimlessly or bounce back in ways that make no sense at all. Seismic data would look like someone just spilled ink on a page, completely chaotic and impossible to interpret. The whole science of seismology would fall apart. Trying to understand an earthquake on a flat Earth would be like trying to read tea leaves from a shattered cup. Predicting aftershocks? Forget it. Understanding tectonic plate movements? Not a chance. You'd be left with seismologists staring blankly at their equipment, trying to make sense of data that just doesn't add up. So, while a flat Earth might sound like a simple concept, the reality is that it would turn something as fundamental as an earthquake into an unsolvable riddle, leaving us all guessing when the ground might shake next. So, you wake up on this newly flat Earth and decide to take a boat trip. Sounds simple enough, right? Just follow the stars like sailors have done for centuries. Except now, there's a slight problem. Those stars no longer behave the way they used to. On our round Earth, celestial navigation is an elegant art. Sailors can trust that the stars will appear in predictable positions depending on where they are on the globe. The North Star, for instance, is a reliable guide in the northern hemisphere, hovering above the horizon at an angle that corresponds to your latitude. It's like having a cosmic GPS that's been honed over millennia. But on a flat Earth, all that logic crumbles. The stars, instead of moving in the orderly patterns we've come to rely on, would seem to shift in bizarre, unpredictable ways. The North Star might appear in different spots, depending on where you're standing on this flat plane, throwing off the whole system. The entire sky would become a confusing mess of celestial objects refusing to align with the neat predictions that once made oceanic voyages possible. Navigation by the stars would turn into a frustrating guessing game. Your trusty sextant would be as useful as a paperweight, leaving you staring at the sky and scratching your head, wondering why nothing is where it's supposed to be. Instead of confidently plotting a course, you'd be adrift, relying on sheer luck to reach your destination, if you even have a clue where that is anymore. In a nutshell, the simple act of following the stars to find your way would become an exercise in futility, thanks to a flat Earth that turns the heavens into a chaotic, unreliable mess. So, you wake up one morning to discover the Earth is flat. After you process the mind-bending implications, you tune into the live feed from the International Space Station, ISS, to see how this flat Earth looks from space. Except wait a second, if the Earth were flat, the ISS would be having a bit of an existential crisis. You see, the ISS orbits the Earth in a smooth, predictable path, providing us with breathtaking footage of a round planet below. This orbit works because the Earth's gravity pulls the station into a continuous freefall around our spherical world. The physics of this setup is like a delicate ballet, relying on the Earth being round to keep the ISS circling it. But on a flat Earth, that ballet would turn into a slapstick routine. First, there's the problem of what exactly the ISS would be orbiting. Without a spherical Earth to keep it in motion, the whole idea of orbiting falls apart. Instead of gracefully looping around the globe, the ISS would either crash back to Earth or, if somehow it managed to stay up there, it would be left awkwardly hovering above a giant disk, unsure of where to go. And let's not even get started on the live feed. The iconic view of Earth from space, the curved horizon, the continents slowly rotating into view would be replaced by what exactly? A flat, static map? A giant pancake? Either way, it would be a pretty underwhelming sight, and astronauts would likely be scratching their heads, wondering what happened to the planet they were supposed to be circling. In short, the very existence of the ISS, with its orbit and stunning visuals, would be impossible on a flat Earth. The station would be grounded, both figuratively and literally, leaving us without that incredible window to our world from space. Imagine waking up to find that the Earth is flat. Besides the initial shock, you'd start wondering how this would affect those distant, icy regions, the polar extremes that have fascinated explorers and scientists alike. You know, the places where it's pitch black for months and then the sun refuses to set for the rest of the year? Well, on a flat Earth, that whole concept goes right out the window. In reality, the unique climates and day-night cycles at the poles are all thanks to the Earth's axial tilt. This tilt means that during certain times of the year, one pole is pointed toward the sun, basking in endless daylight, while the other is plunged into darkness. It's a beautifully simple explanation that also accounts for why these regions are so extreme. with vast ice caps and some of the most challenging conditions on Earth. But if the Earth were flat, you'd need some pretty convoluted, arbitrary explanations to recreate those extremes. The whole idea of one pole being bathed in sunlight while the other is in shadow just doesn't work on a flat plane. You'd have to invent some bizarre mechanism to explain why parts of this flat world experience such drastic differences in light and temperature. And those ice caps? They exist because of the way the poles are positioned relative to the sun on our round Earth. Without the tilt, you'd have to come up with a reason why certain areas are perpetually frozen while others aren't. Maybe someone would suggest a giant sun lamp over the Arctic and a freezer blasting the Antarctic. Both ideas equally absurd, but necessary to maintain the extremes we see on our spherical planet. So, while the idea of a flat Earth might seem straightforward at first, it quickly unravels when you try to make sense of the polar regions. The extremes that are so naturally explained by our planets, tilt would become an unsolvable puzzle, leaving us wondering why the world suddenly stopped making sense. Imagine the Earth suddenly went flat overnight, and you're the captain of a submarine setting out for a round-the-world journey. Sounds like an adventure, right? Except now, your underwater navigation is about to turn into a nightmare. Submarines rely on the Earth's curvature to navigate the oceans. As they glide beneath the waves, the curved shape of the planet provides a natural reference for their instruments, allowing them to calculate their position accurately and plot a course across the globe. It's like driving on a road that gently bends and dips, guiding you to your destination. But on a flat Earth? Well, that whole system falls apart. Without a curved planet to follow, your submarine's navigation equipment would be completely baffled. The instruments designed to measure depth and distance based on the Earth's curvature would give you readings that make no sense. Instead of smoothly navigating from one continent to another, you'd be left wondering if your submarine is even heading in the right direction. And what about the idea of actually completing a round-the-world trip on a flat Earth? That phrase would lose all meaning. You'd either end up bumping into the edge of this pancake world, or, more confusingly, sailing off into some endless ocean with no curve to guide you back. The very concept of circumnavigation becomes a head-scratcher, leaving you and your crew wondering if you'll ever make it home, or if there's even a home to return to. So, while a submarine might seem like the perfect vessel for exploring a flat Earth, the reality is that underwater navigation would become an impossible puzzle. The technology designed to navigate our spherical planet would be utterly lost, just like you would be somewhere in the deep, flat sea. So imagine the Earth is suddenly flat and you're trying to check the weather forecast. You turn on the news, expecting to see the usual satellite images of swirling clouds and storms. But instead, there's just static and confusion in the meteorologist's eyes. Weather satellites rely on the Earth's spherical shape to do their job. They orbit the planet in precise paths, capturing images and data from every angle, creating a comprehensive picture of global weather patterns. These satellites follow the curvature of the Earth, making sure they cover every region as they loop around, giving us accurate forecasts and warnings. But on a flat Earth, those carefully planned orbits wouldn't make any sense. The whole idea of a satellite circling a flat plane is absurd. Where would it even go? Instead of smoothly orbiting and collecting data, these satellites would either crash down to Earth or drift off into space, unsure of what to do in this strange new reality. Even if you managed to get a satellite up there, the data it collected would be a mess. Without a spherical Earth to orbit, there's no way to get a consistent, comprehensive view of the weather. You'd have gaps in coverage, chaotic data points that don't align, and a complete inability to predict what's coming next. Imagine trying to track a hurricane when your satellite only captures random slices of the storm, leaving you guessing at where it's headed. In essence, on a flat Earth, weather observation would be a lost cause. The satellites we depend on would be grounded, both figuratively and literally, leaving us with nothing but guesswork to predict the weather. So, next time you see those beautiful, sweeping satellite images of a storm, just remember, they're brought to you by a planet that actually makes sense. As we've explored, the idea of a flat Earth leads to a lot of puzzling questions and scenarios that don't quite add up. From gravity pulling in strange directions, to the confusing time zones, and the unexplained disappearance of ships over the horizon. It's clear that our round Earth makes a lot more sense. Thank you for diving into this thought experiment with us. If you enjoyed this video, give it a thumbs up and don't forget to subscribe to Quiet Universe for more mind-bending explorations. Together, let's keep wondering, questioning and discovering the wonders of our incredible universe. See you in the next video.